Howdy, everyone. Give just a minute as people trickle in and find their way. So, remember, we have this outline due on Friday. So that will be informed by the intro video that you gave in terms of what you're thinking of doing, how much you think you have time for. The outline should have a rough layout of how much time you think each piece is going to take. So you can approximate, I think this piece is going to take 5 minutes to go over or whatever. As much as you can, you want to include in your outline anything you already have nailed down. So things like statements of definitions, statements of theorems, any particular examples that you already happen to like. All of these kinds of things you want to, as much as possible, put in your outline. Now, most likely when you actually go to record your video, you'll be talking from some maybe modified version of the outline you're showing me. But the outline you're showing me is basically a sort of like a sketch of what the finished product is going to look like before you go ahead and actually start implementing the finished product. Okay. You had this homework assignment due on Friday with Sage stuff. I got a few questions with that, but I'm going to assume that mostly went well. In lieu of everything going on outside, I'm going to go ahead and say that we're going to do the quiz Wednesday instead of today. So remember, the quiz is going to be over the Chinese remainder theorem and primitive roots. So take care to prepare for that. All right. And my microphone is actually on. Good. I was briefly afraid that my microphone was off. Okay. So our goal today is to talk about RSA. So I sort of outlined RSA last time, but I want to talk about RSA in more depth today. Go through and write out the entire process for you. Make sure we understand why it works, what it does, all of these kinds of things. And then if there is time after that, then we can spend some time talking about factoring as an algorithmic problem. Right. If you have any questions throughout today's lecture, just put them in the chat and I will do my best to respond to them as I go through. Right. So the most important piece that underlies RSA is this theorem that tells us what the period of exponential functions is mod a composite that's a product of two primes. So if P and Q are distinct primes, n is equal to P times Q, and a is just some integer, then the period of a to the x divides, and we gave this name lambda to this thing, which is defined to be the least common multiple of p minus 1 and q minus 1. And our proof here was entirely based on the Chinese remainder theorem. Basically, we said, okay, how much time is it going to take for this thing to repeat mod p? Well, mod p, we know it repeats every p minus 1. Mod q, we know it repeats every q minus 1. And so, in fact, mod pq, it repeats every time we have a number that is divisible by both p minus 1 and q minus 1. And those numbers are exactly what we mean when we talk about the least common multiple. Okay. So this is, again, I'll remind you, an analog of Fermat's little theorem, which just told us about what's happening mod primes. And so the foundation of RSA is, in summary, someone who knows n can't compute lambda. Without first factoring n. So the hard problem that underlies RSA is factoring, and this is the way that we sort of hide this complicated combination of thing that's easy for us to compute but hard for someone from the outside to compute, is that if we only know the product of P and Q, we can't compute lambda. But if we actually know P and Q, then it's very easy, because remember, a least common multiple calculation is basically equivalent to a GCD calculation, so it is very, very fast. Okay, so let's outline RSA now. Okay, so here we're going to say Alice wants to send a message to Bob, or Alice wants to send a message from Bob. I forget which one I said last time. Let's say Alice wants to receive a message. Okay, so Alice has to do a lot of preparatory work. So the first thing Alice has to do is generate two large primes, P and Q. Okay. So then Alice is going to calculate and publish n, which is going to be the product of P times Q. Okay, so I will try and box in blue things that are public. Okay, so n is public. And Alice will also calculate lambda. Alice is going to choose some e that is relatively prime to lambda. Okay. So, simple note about e. E is relatively prime to the least common multiple of P minus 1 and Q minus 1. And while P and Q are both primes, and they had better be odd primes, because, spoiler, this will not go well for you if you try and do this if one of P and Q is 2. And so because P and Q are both odd primes, the least common multiple of P minus 1 and Q minus 1 is always going to be divisible by 2, so this lambda has to at least be odd. But if you happen to also have other factors here, which you likely will, then you also have to dodge all of those factors when you're writing down this lambda. Okay, and then Alice publishes this E. next, and this is all pre-work, this is all before anyone is actually doing any communicating, Alice is going to calculate D which is going to be E inverse mod lambda. Okay, so just to outline here, what pieces of this are part of what we call the public key? That is, what are the things that people need to know to send messages to Alice? The public key really only has two simple pieces. The public key is N and E. So in order to send messages to Alice, we're going to see that all someone needs to know is this public key, these two pieces of information. And then the private key, that is the thing that only Alice knows, is D. Now, you might think, oh, well, P and Q are also sort of part of the private key, or lambda you might think of as being part of the private key. And all of those are pieces of information that only Alice knows. Only Alice knows P, only Alice knows Q, only Alice knows lambda. But in fact, actually, once Alice has calculated D, this is the only information she needs to know beyond the information in the public key. So Alice could actually, at this point, forget what P and Q are, and it would not matter. That said, there is no additional security in Alice sort of forgetting this other information, because if you know D and E, then you can factor N. And we'll again talk about that on the next homework. Okay, so step one is actually a lot of steps, but that is just all the work that has to be done before you can use RSA. So maybe you could call that step 0 if you wanted. So then, step 2, now we go to Bob. And so Bob is going to encode his message as some integer m mod n. Remember, if Bob's message is too long to encode as a message mod n, this n, by the way, it's the same n from the public key, just to emphasize. If the message is too long to fit into a single integer mod n, then Bob just breaks the message up into pieces until it fits. Okay, next, Bob calculates and publishes, or if you want to say sends to Alice, m to the e mod n. Okay, so let's just recall where all of this information is coming from. E and N are both pieces of the public key. So literally everyone in the world knows N and E. Okay. D is a piece of information that is private to Alice. And M, the message, is a piece of information that is private to Bob. So really, there's only these four pieces of information to keep track of: the modulus n, the encryption exponent e, both of which are the public key that everyone knows, the private key, which is Alice's d, and the public key, and the message, which is Bob's m. Okay, so the way I said this is that Bob just makes this information m to the e public or sends it to Alice, whichever way you want to think of it. Basically, when I say someone sends something to someone else, we're meant to imagine it sort of bouncing around the internet, and so anyone who wants to can sort of snoop on that information, and so anyone who wants to really could have the m to the e. But the idea is someone who has m to the e can't infer any information about m, for example. Okay, so finally, Alice calculates m to the e to the d. And this is always m. And so in this way, Alice learns Bob's message. Okay, now someone in the chat tell me, why is m to the e to the d m? So it's because d is E inverse, but d is E inverse mod the right thing. So m to the e to the d is m to the e times d. And so we want to say, and this is in a sense correct, that, okay, so because d is E inverse, E times d is 1, so this is equal to m to the 1, and so that's m, and that's y. Okay. The important thing to emphasize is, where is this exponent of m happening? Okay. And this is where we need to know about the period of m to the x. So remember, I've emphasized this before, but I want to reiterate, the modulus of the exponent is not the same as the modulus overall. So the modulus overall is what we've called n. But I cannot interpret this x mod n. The actual modulus of this x is the period. And this is why, before we could talk about RSA, we had to talk about this theorem that tells us what the period is of some exponential mod p times q. And in this case, that modulus, or that period, we know it divides this lambda, the least common multiple of p minus 1 and q minus 1. Okay. So this divides lambda. And when I say the period divides lambda, that means every lambda that happens in the power just washes away, because this thing repeats every lambda over and over and over again. And so what that really tells us is that the exponent makes sense mod lambda. And this is why it's important that, in fact, D is E inverse mod lambda. Now, note if D was E inverse mod n, that would be really bad, because someone who's watching could calculate could calculate D, right? Because anyone could calculate E inverse mod n. And hey, E probably has an inverse mod n. It's just not the useful thing to have. Okay, questions about this? Okay, so let's go ahead and just, for fun, let's ask ourselves what algorithms that we've learned so far does implementing RSA rely on? Okay, so let's just go through this algorithm let's just go through this outline that I just wrote, and let's pick things out. Okay. So the first thing Alice had to do was generate two large primes. So that means the first thing we need is primality testing. And we have a very good primality testing algorithm. Remember, that's the Fermat test. I continue to promise you I will give you a slightly better primality testing algorithm than the Fermat test, but I hope you saw from the homework just how efficient the Fermat test is and how effective it actually is, to see that, okay, it's not the case that the Fermat test is constantly leading you astray. In fact, there was this, one of the questions on the homework was sort of like, find the first two pseudo-prime, and you had to pass by thousands of primes before you found a pseudo-prime. And that was only one that was pseudo-prime to one base, not even one that was pseudo-prime to, say, the first 4 or 5 bases that you thought to check. Okay. So, primality testing, we can do this quite well. Alice next multiplies. We don't really worry about the fact that Alice knows how to multiply. But next we have to calculate the least common multiple, which again really requires the Euclidean algorithm. Okay, and I'm going to be very explicit here. What is it that you do to calculate the least common multiple of p minus 1 and q minus 1? You calculate p minus 1 times q minus 1, and then you divide it by the greatest common divisor of p minus 1 and q minus 1. Okay, and so the Euclidean algorithm handles the calculating the GCD of p minus 1 and q minus 1. Next up, we need the extended Euclidean algorithm to calculate E inverse mod lambda. please note, by the way, the reason why Alice needs to choose an E that is relatively prime to lambda is because the next thing Alice is going to do is to calculate the inverse of E mod lambda. If E is not relatively prime to lambda, then E won't have an inverse mod lambda, and this whole thing will break. So this is a very real requirement. Alice really needs to make super sure that whatever E she has chosen is genuinely relatively prime to lambda, or this next step won't work. Okay, so that was just Alice's work, and Alice has already used these things. Next up, Bob is going to encode his message as an integer, and then send Alice m to the e mod n. Now, you might be inclined to say that this requires repeated squaring, but this step doesn't necessarily require repeated squaring, because in fact, e is not actually necessarily required to be large. In fact, you might deliberately choose e to be as small as possible. So for example, you might choose e to be the number 3, so that the person who's sending you messages has to do as little computation as possible. Okay. But even something like e is 3, as long as the person who's sending the message is following good protocols, will suffice to blind someone who's looking at this to being able to decrypt what it is. Okay. But regardless of whether e is big or small, Alice definitely needs repeated squaring to calculate m to the e to the d, because this decryption exponent will always be large. Okay, so I believe, actually, if you look through this, this is just a list of all the algorithms that we talked about in the last chapter. So I think RSA really uses just about all the algorithmic number theory that we have done so far in order to actually implement this. And it is completely essential that, in fact, computationally, all of these pieces are easy. Because if, in fact, all of these pieces weren't easy, then you wouldn't be able to actually do this. Okay, I'm going to pause just a moment and see if there's any questions, and if there are no questions, then I will continue. It is also worth asking what an onlooker here sees. So we've carefully nailed down what information Alice has and doesn't have, and what information Bob has and doesn't have. But let's think about a third party. So what does Eve see? Okay. Eve usually chosen because it sounds like evil. So Eve, who is looking on, definitely sees all the public key information. That is, Eve sees N and E, because those are both public. what else does Eve see? Right. Eve also sees m to the e. That is right. So Eve sees n, e, and m to the e mod n. And note, if you're actually using this to send a longer message, then there might not just be one message. It might be that actually Eve sees, for example, m1 to the e mod n, m2 to the e mod n, and so on. So Eve may, in fact, get to see lots of different encrypted messages, encrypted with the same n and e. What is the most expensive part of this algorithm? What is the part that requires the most work in order to implement this? And who has to do that work? Calculating lambda, and actually something before we had to calculate lambda, I think it's actually the generating the primes is the hardest part. So as you saw in the homework on Friday, probably it actually took you a fairly long time on some of these questions. I think there were 2 questions on the homework that said, give me a 200-digit prime where blah, 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 or whatever. It might actually take you quite a while to generate a large prime. Not because our prime detection algorithm isn't good. Our prime detection algorithm is quite good. But primes are pretty rare, so even if the primality testing algorithm itself is fast, we still might have to try thing after thing after thing after thing after thing in order to actually find these 2 primes that work. Okay. But the answer is correct. Alice is the one who has to do all of the computationally intensive work. You can actually rig it so that, in fact, Bob has to do no computationally intensive work. For example, the most Bob has to do might well be to cube his message mod n. Now, I want to point out one disadvantage to having a small e, because what I've just said is a very large advantage to having a small e, which is that if your e is small, it makes it easy for someone to send you messages, which, again, for these chips and credit cards like we keep talking about, or these other like really tiny computers that are in things, actually sending the message might be the only thing it needs to be able to do. And that's a huge savings, because then all the hard work is getting done on the other side, and we don't care about that. But you have to be super careful, if you're choosing a small e, that you don't interpret your m too directly. Okay. So let's imagine that what you're sending is a credit card number. And let's imagine that e is 3. Okay. So if e is 3 and m is a credit card number, What might go wrong here? Well, how many digits is m? Yes, someone in the chat notices. Yes, so M is somewhere in the vicinity of, is a credit card number 15, 16 digits, somewhere in that vicinity. I think it depends on the credit card brand, but I think it's 15 to 16 digits. Okay. N, on the other hand, if you're taking a 4096-bit RSA key, which is, I think, the standard, that's over 1,000 digits. Okay. And so as a result, if I just do this naively, m cubed mod n is just m cubed. And wouldn't you know it, if the number you're looking at is actually m cubed, you can just calculate the cube root of it as an integer, like a plain old regular integer. So Eve could cube root this. The moral of the story here is something that's actually true about public key systems in general. And this is definitely a point that is more on the computer security side than on the mathy cryptography side, but it is worth emphasizing the sort of overlap between these. Never, ever send a short message with a public key system. Okay, here's one reason. It might take a problem that was supposed to be computationally difficult and make it easy, as is the case here, because someone can actually just calculate the cube root. But you also run the problem that the public key is public. And so that means one thing Eve can do is that Eve can just try a bunch of messages that she thinks Bob might be trying to send and see if she matches the m to the e that she saw from Bob. So imagine that Eve sees Alice ask Bob, hey, do you want to go to the movies tonight? Eve can imagine what Bob's responses might be. Bob's responses might be yes, no, maybe. And maybe Bob will put a period or not. And so Alice could generate a list of, say, 100 different possible responses that Bob might give to this question. And then what can Eve do? Eve can encrypt all 100 of those. And then when Bob actually does respond to Alice, Eve can look at this m to the e that Bob sends and see if it matches any of the messages that she guessed that Bob might send. And if it does, then even though Eve didn't break the system in some literal sense, Eve definitely figured out what message Bob sent, and well, that's sort of the whole point of this, is for that not to happen. Okay. So, how do you fix that? How do you make sure that Eve is never able to guess Bob's message? And how do you make sure that if you want to send a short message, how do you send a short message without sending a short message in this sense? So any suggestions in the chat as to what you might do to sort of shore up this security vulnerability? Yes, so that's exactly what you want to do. You want to pad your message with random bits. Okay. And often a source of random bits is that you will send a timestamp that is accurate to like microseconds or something, so someone's still not going to be able to guess what it was. But you basically look for some source of making it a non-deterministic message, so that even if your answer is yes, you spend 8 digits of your message saying yes, and then you spend the remaining 1,000 digits of your message throwing in random zeros and ones, so that Eve can't possibly guess what message you were actually sending. Questions about that? There is a second security reason why you probably want to include timestamps in messages. And the second reason is that, again, if you imagine Eve is sitting here watching all of this happen, when Eve sees m to the e mod n, Eve now knows that this is a message that means something. And she might be able to infer what kind of message this is. And so something that Eve could very easily do, if there was no timestamp included in the message, is to, a few months later, send Alice the message m to the e mod n and see what happens. And so you definitely want it to be the case in practice that if someone resends you an old message, that it is obvious to you that you are looking at an old message and not a current message, because you don't want someone else sending you messages that don't get caught. So, for example, if you imagine that you submit an Amazon order and someone were able to track that, you could imagine that they send your Amazon order for a book to Amazon like 1,000 times, and now you get 1,000 copies of the book or something like that. I'm not sure exactly what they get out of that, but you don't want that to be able to happen. You want to be able to catch it if someone sends a message out of time. Okay. Uh, I want to talk about one more use for RSA that is very cool and that we've basically done all the math that we need to for, which is digital signatures. Okay. So the purpose of a digital signature is much different than the purpose of a cryptosystem. The purpose of a digital signature is to post a message publicly that people know came from you. Okay. So, for example, if, let's say, the dean says this student can graduate or whatever and sends a message to the registrar's office that says so and so can graduate, the dean or whatever, the source of this message is really important. Because nominally, anyone could send this message and anyone could sign it the dean or whatever. And then, well, that would be a problem. Okay. So the goal here is to be able to verify that this is the real sender. Okay, so how do we go about this? So let's just, to put this back in our fantasy universe with Alice, Bob, and Eve, let's imagine that Alice is the dean. Okay. And remember that Alice is publicly associated with her combination of public key. So that is to say, in this fantasy universe where Alice is using this RSA key to correspond with a bunch of people and get sent messages by them, there is a publicly maintained list somewhere that says, hey, Alice is associated with this N and this E. And that's something that you can see from this public registry. Only Alice should know the private key that goes with N and E. Okay. So the key is, key is a terrible word. The way that digital signatures work is that Alice can prove she knows D, the decryption exponent, without actually publishing D. Okay. And so the way Alice signs a message she actually publishes M to the D mod N. And just for emphasis, this here is a D. So in terms of everything we just said, this doesn't really make a lot of sense. D is the decryption exponent. When you get an encrypted message, you're supposed to raise it to the dth power to decrypt it. But now what is Alice doing? She's actually, in a way, encrypting a message, but with her private key. But here's the special thing. Now anyone can calculate m to the d to the e mod n. And guess what? If m to the e to the d is m, so is m to the d to the e. And so anyone in the entire universe can find Alice's message, M. Okay. And now, at first, that seems kind of backwards, because the whole point of our cryptosystem previously was to send a message that no one could break. But now, our goal is to send a message that everyone can see, but that we know comes from Alice. And when someone calculates this m to the d to the e and gets a sensible message here, well, the only way anyone could have found something that when raised to the eth power gives you a sensible message is if that person knew D. And hence, if someone is able to post a coherent message after doing this, that person must be Alice, because they have to have known Alice's private key. Okay, and so to say that more precisely, someone who sent this must know Alice's private key. Okay. Questions about this digital signature part at the end. I know that this takes a moment to convince yourself that this really works, because it seems, I mean, it's almost identical. It is painfully close to identical to regular RSA. But does it make sense how Alice can sort of fake encrypt her message so that someone who decrypts it knows it definitely came from her? Again, I want to reiterate here, it's really important to actually any public key system, but it's important to the digital signatures, it's important to RSA, it's important to El Gamal or whatever. It's important that there's some trusted authority that keeps track of public keys. So basically, it's like a Yellow Pages, but instead of giving someone's phone number, it gives their public key so that you can send that person information. And so there's an awful lot on the security side that goes into making someone able to be that figure and making sure that people can verify that, hey, yeah, this person is who they say they are. Now, it also bears repeating that if someone somehow is able to factor Alice's n, then they can also calculate d. So if someone somehow manages to get, say, really lucky and they factor Alice's RSA key, or maybe it turns out that factoring is actually easy, we just haven't found the right algorithm for it, or whatever, then it may well happen that someone is able to figure out what this is, and then they can decrypt all the messages that are sent to Alice and all of these kinds of things going forward, which is why you might, for example, want to change your public key with moderate frequency so that even if one of them is compromised, the next one isn't necessarily. And as we'll see in this next section, it's going to turn out that there's actually a lot of primes where it might be easier than you'd think to factor this product. As a last note today, and we'll pick up with this on Wednesday as well, I wanted to talk about the birthday problem, which is something that's actually well enough known you've likely seen this before. But it is how many people have to be in the same room before the odds are that that two of them have the same birthday. And now, it's not uncommon to think through this and think, well, there's 360 possible birthdays. So definitely if I get to 366, well then definitely there's two people with the same birthday. But that's 100% probability, not 50% probability. But then it sort of feels like, well, maybe the break-off is when sort of like there's half as many people, so like 180 people or something like that. And that's a pretty intuitive thing to do. It just turns out it's completely wrong, because the actual answer is 23. Okay. And the point of this is, hey, this number is pretty small relative to 365. That's an exclamation point, not a factorial, although I guess it's also true if that's a factorial. Okay. And there's a good reason why this number's a lot smaller than you might at first think. And that's that you might be sort of thinking about this 1 in 365 number. So the probability that two people have the same birthday should be 1 in 365. I'll note, by the way, I'm not in this calculation assuming that, like, oh, actually there's more people born in February because blah, 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 blah. I'm not calculating any of that. This is just purely imagining that everyone has a 1 in 365 chance of having a particular birthday. Okay. And so you might think it takes a lot of 1 in 365s to get to greater than 50%. But the key thing is, in a room of people, you don't get 1 365 for every person. You actually get one of these basically lottery tickets for every pair of people. So in other words, in a room with 23 people, I'm not getting 23 chances at a 1 in 365 probability. I'm getting 23 choose 2 chances, which happens to be 23 times 22 divided by 2, or this number, if you have taken probability or whatever. And this number is actually pretty close already to being over 300. So, as it's going to turn out, some of the better algorithms for factoring and some of the better algorithms for discrete logs that we're going to talk about this week are based on this fact that you get what are called collisions relatively very quickly when you draw out of the same pool. Okay. But I'll wrap up there for today. Remember about the quiz for next time. I will post the homework for this section up through RSA by Wednesday. But until then, have a wonderful afternoon, and I will see you on Wednesday on campus when hopefully the world will be less white. Have a good afternoon.